Hey everyone, it's Dr. Walker. In this video, we're going to go over the second example from video 579 on solenoids and toroids. In that video, we showed an expression for the magnetic field inside a solenoid. We said that a solenoid was a wire that was turned into a whole bunch of loops, right? A whole bunch of loops. And we showed that the field inside was approximately constant, especially if you have a long solenoid. Just to go back to that picture really quickly, this is what we saw, that there is a very weak field outside, but there is going to be a very strong field that's approximately constant inside that solenoid. So let's go ahead and use Ampere's law to derive this expression. We're going to take the line integral of B dot ds, and that will equal mu naught times the current that is penetrating that surface made by that Amperean loop. So what type of Amperean loop do we want to take account for the symmetry? Well, the field is straight, so it's going to make sense to pick a rectangular Amperean loop. Let's pick a loop that is partly inside the solenoid and partly outside. Rectangular loop here. And let's look at the integral. Let's look at one side at a time. Let's start with side number 3. We said that the field is very weak outside the solenoid. We can say it's practically 0. So the B dot ds, that integral is going to be 0 for path 3. Let's say that we're going clockwise here, since if the field is basically 0. For paths 2 and 4, that little element ds is, well, when we're outside the loop, the field is still 0, so we still have 0. But what about when we're inside the loop? Well, that ds is going to be perpendicular to b, so the dot product is also 0. So for the path 2 and 4, that also gives us 0, so that means that we're really only going to look at path number 1 when we're doing that line integral. When we do that path integral for side 1, then the ds is going to be parallel to the field at all times. So, and the b is going to be constant along that path. So we're just going to get b and then an integral of ds along the whole length. The whole length, we can call it capital L. I changed the picture from lowercase to uppercase capital L to match the expression that I found in the video earlier. So we have b times L. And then we need the current that is penetrating our surface, and right here all of this current is penetrating the surface. We can make a surface like this with this Amperean loop. So if the solenoid is carrying a current I, then we have 1, 2, 3, 4, 5, 6 times I, but let's just say that we have n loops here within our Amperean loop. Then the current enclosed, or the current penetrating, is going to be n times I, where n is the number of loops enclosed within that Amperean loop. When we solve for b, we're going to get mu naught n over Li, which is the expression that I showed above. But often we say that n divided by L, which is the number of turns per length, we call that little n. So we can also write the field inside of a solenoid as mu naught Ni, where n is equal to the number of turns per length. The next video we will do an example with a toroid.